Imagine a robot not in some gleaming lab, but deep inside a collapsed mine. The air is thick with dust, every second counts, and the path ahead is a chaotic labyrinth of twisted metal and shattered concrete. Its mission: find survivors. But to do that, it needs to understand this terrifying new world instantly, to map every crevice and corridor in perfect 3D, and to know its own precise location at all times. This is the frontier of robotic navigation, and a team of MIT researchers just shattered a major barrier. For years, robots have relied on a technique called SLAM, simultaneous localization and mapping. Think of it as the robot's sense of sight and internal GPS combined. But traditional SLAM has a fatal flaw. It chokes in complex, cluttered environments. It often needs pre-calibrated cameras and can get hopelessly lost. Then came machine learning, which simplified things but introduced a brutal limitation. These new AI models could only process about 60 images at once. In a real disaster site, a robot might capture thousands of frames in minutes. Waiting for it to slowly crunch the data just isn't an option. It was a classic case of speed versus accuracy, a trade-off that could cost lives. They had the AI break down a massive, complex scene into smaller, more manageable chunks, like puzzle pieces. These are called submaps. The system builds these mini-maps incrementally as the robot moves. But here's where they hit a wall. When they tried to stitch these AI-generated submaps together, they just wouldn't line up properly. The machine learning model, for all its power, was introducing subtle distortions, warping the digital reality just enough to make the final map a messy, incoherent jigsaw. The breakthrough came not from abandoning the new AI, but by marrying it with the old guard of classical geometry. As grad student Dominic Maggio discovered, you can't just force these warped pieces together with standard methods. Professor Luca Carlone explains they needed a mathematical framework that could understand and correct these deformations, bending each submap back into shape in a consistent way before seamlessly stitching them into one perfect, coherent 3D model. It was the missing link. By bridging the intuitive power of machine learning with the rigorous precision of classical optimization, the results were immediate and stunning. In a breathtaking demonstration, they simply took a short cell phone video walking through the chapel's interior. Within seconds, their system reconstructed a hyper-accurate 3D model of the entire space with an average error of less than 5 centimeters. No special cameras, no complex calibration, just a video from a device in your pocket, processed almost instantly into a perfect digital twin. This same technology could power the next generation of wearable AR and VR, allowing your headset to understand and map your living room in real time. It could revolutionize warehouse automation, with robots that can dynamically map and navigate vast, ever-changing inventories. The key insight, as Carlone puts it, is that knowing about traditional geometry pays off. Deep understanding of the underlying model allows you to build something that is not only smarter and faster, but also beautifully simple and scalable. This is how we build the future, not by choosing between new and old, but by fusing them together to create something truly revolutionary.